Wreck yourself. Hey, my name is Carl Eriksson and I work at Svenska Elektrod. We are a certified system integrator for Universal Robots as well as a partner of Nordbo Robotics. And that's why we're here today. I'm going to talk to you about the Mimic. Mimic is a platform developed by Nordbo Robotics that enables us to do programming without actually programming. We're actually having the robot mimic our movements, hence the name. It is a no-code platform that uses different types of mimicking features to translate what we're doing as a skilled worker into the movements of the robot. What I've got here is a setup with a Schunk AOV orbital sander. It has compensation, both in actual direction, both positive and negative. Today we're only going to be using the positive direction. Of course, we then have our feed of spindle air and compensation air, which is directed through a little tree of valves, etc. here, everything connected to the robot. What we've got over here, and what I'm going to be talking a little bit more about, is a joystick that can be used for many different things. But in this application, I've actually copied the bottom of this orbital sander to make sure that we are mimicking something that's actually relatable to real life. On top of this joystick, you'll see there's a fitting for something, and I'm going to get back to that later. What we got over here, the green lighting over here, this is an infrared beacon. So what this does is it's sending out an infrared light and then detecting anything in the viewing field of this beacon, and then, in this case, mimicking that. So I'm going to pick up the end piece of the puzzle, which is over here. Now, this is what we're using. This is an HTC Vive, which is basically what you're going to be using if you're doing VR gaming, for example. So this is a readily available product off the market that we're using together with the Mimic software. This then goes on top of here. So these plugs in this joystick, mounts the HTC Vive. And now, when the beacon sees this, it actually mimics everything I'm doing. And I'm going to show you in the software how this works. So here is the installation files for the Nordbo Mimic URCAP. I can actually bring it up so you see what I'm doing. It connects via Ethernet IP, so we have an Ethernet cable in between a little NUC computer on the control box of the UR. And we're setting which kind of tracker we're using. So as you can see, there are multiple choices here. We have IR tracker, which is what we're using now, infrared. EM, electromagnetic tracking. Now, this is not going to be gone through in this particular series, but this is when you have a lot tighter tolerances and within a more narrow workspace, then you can use the electromagnetic tracking instead. Then we have the FT tracker, which we're also going to go through, which is the force torque sensor. So instead of using light, infrared in this case, we can use a force torque sensor to actually guide the robot to what we want it to do. Now, we're going to use the IR tracker, and the first thing that we always need to do is to align the tracker. So, the tracker, this one, I'll toggle it on and make sure that the light is green, which means that this one is seen. This one is seen by the beacon. Now, I'm going to put this in the little mounting that I have down here. which is then aligned with the robot axis. So I have a little alignment pad here, which is positive y and positive x. Now you might think, why, that's a strange coordination for this kind of surface, but the reason for it being that if we go over to the universal robot, the positive y of the robot axis is always where the robot cable comes out of the base. So that's why we have aligned the tracker with that now. I'm going to go over another orientation feature later, but this is what we're going to do for starters. So once that's in, once we know that it's seen by the beacon, we just hit Align Tracker. There we go, successfully calibrated tracker orientation. Now, we're actually good to just do the simple first thing that I can show you and to get you understanding how the Mimic works. So we're going to open up a new program, and we're going to go into the UR caps and select what's called the track. Now, the track is one of the ways to use the Mimic. There's track and there's teach. Track will automatically translate anything you do simultaneously into the robot arm. Meaning that we could do some sort of work on a workpiece, and we could have a second workpiece sitting next to us. So we're doing the same movements on one workpiece and the robot is doing it on the next one while we're teaching it. The other one is teach, and we're going to go through that in depth. But first of all, I'm just going to show you the features of Mimic with track. So first of all, we need to choose a name for our track, and we'll call it AOV test. Then we choose the robot TCP, and now the robot TCP is calibrated to be the same as the tool, which is here, with a little bit of compensation, not fully extended, but not fully retracted either. Then we choose which joystick, and I'm going to come back to this, and if we would have a conveyor that we would need to track simultaneously, we would choose that as well. Now if we go into the runtime view, and we just hit play, we're going to see what happens. So I'll take my HTC Vive module, I'll put that on my joystick, and then we're just going to move this and actually just have the robot do anything that I do, like so. So you can see up and down movements, like so, or side to side, simultaneous. Even if I'm rotating, it's doing the exact same thing, pivoting, all angles, meaning that this translates exactly my movements. If I now let go of a button that I'm going to talk to you a little bit about, and I move somewhere over here where the tracker is still seen by the lighthouse, it's still going to mimic the movements in real time. So it doesn't matter, I moved so it didn't see it, anywhere that I stand, as long as the beacon sees, it's going to translate all my movements simultaneously when I hit this button. So on the side of this joystick, you'll see a number of buttons. You'll see this one, which is the one I'm using to move right now. You'll see this one, you'll see this one, and you'll see this one. And all of these buttons are readily adjustable if we go into the software in the installation tab and we go into joysticks. So if we go into setup and joystick, and then we go into AOV IR, which was the one you saw me use. I go into edit to watch it. Then you'll actually see these buttons that I was talking about. The round one, the triangle one, the diamond shaped one, and the square one. Here, I can define exactly what these are going to do. For example, right now I'm using it in this sanding application. Maybe I want to turn on the spindle using one of the buttons. I could define that just going into this button and then tell the robot what it should do. So right now it's using the server input, meaning that we're doing the mimic function, but we could also use this to set, for example, a robot digital out 1, which means that now we're actually triggering the sanding, because digital out 1 is in our program controlling the air to the spindle. Now we're not going to do that, but just to show you what's possible. We're going to go back to move. And the other things you'll see here on the left-hand side is the calibration of the joystick itself. So we've 3D printed the feature on the base here to be exactly as the tool itself. Then we've calibrated the TCP on the bottom of this to be in relation to the HTC Vive. And these are the calibration data that you see here. So we have, if we go into RPY degrees instead, it's minus 155 degrees on rotational X. We have 88.2 millimeters in Y, and we have minus 149.2 in Z. Then we've saved this as a joystick, and we've used this. Now, this is the joysticks, and we can do as many joysticks as we want. We can do a lot of different features. If you want to have a spray painting gun, for example, we calibrate that instead, or any other manual tool that you want the robot to mimic. The other thing that we can do, and that's what we're going to do now, we're going to teach the system in teach mode instead of track mode. Now, in order to do this, we need to have a reference frame, something where we're going to be doing the teaching. And these are called reference frames. Here we have a reference frame called svetsbord, which is welding table in Swedish. And that's this table right here. If we go into the data of that table, you'll see that that's actually translated to the orientation from the robot base. So you remember I told you that the positive y-axis was this direction. You can also see that in the software on the image. But I then have my origin down here, and I know the measurements of this table, so you can do this in two ways. Either you move the TCP of the robot to these locations and track the actual feature, and then mount this, of course, readily or steadily to your table. But in this case, I know the points here. So I'll just put them in, and in the software, I've already set them to be positive X, 1050 millimeters. I've put them to minus 1100 on Y, and minus 125 on Z. And that's because the robot is mounted elevated, 12.5 centimeters. Now, if we go in to a program, we remove our track, and we choose a teach instead. And we still need to name this trajectory, so we'll do AOV teach test. Just before doing that, we can just test that the outputs are working as they should. So we go into the I/O setup, and I've named the two outputs that we're using, compensation and spindle. So compensation, yep, working as it should, and then spindle, working as it should. So we're ready to go to program this grinding application that we got over here. So I named the trajectory AOV teach test. Then I've set my joystick to AOVIR, which is this one that you've already seen. Now, what we always need to do in the beginning of a teach is to align this with our reference frame. And that's why I told you about the orientation down here, because it's important now that this is not aligned as we're doing in track, but this is actually aligned with the origo, or the center point of this reference frame coordinate system, because otherwise the teaching will be off. So I'm putting this down here, making sure that it's green and green. Then I'm starting the program. Then it's going to tell me to please place the tracker in the reference plate. Yes, I've done that. And then click calibrate to make the teaching frame. Calibrate. There we go. Easy as that. Now we're actually ready to take this out. We're putting that in here. And now we're ready to teach. And as I set the blue button over here to be recording, I'm going to use that button to start record. So what I'm doing here is I am pressing recording somewhere in the vicinity of where the robot is. And now I always need to make sure that the orientation of the joystick is aligned with the way I want this one to be aligned, because otherwise it's not going to work, okay? So, I'll start the recording by pressing... Nope. So what I was doing there was that since I was turning away, I was covering the signal, which means that the software cannot pick up the signal. So I need to recalibrate that. Like so. Press calibrate. Then we're good to go. So I press the blue button to start the recording. And then I move into the positions that I want to be doing. So I'm going to do the front first. I'm going to go up against it. I'm going to go over it like so. Then going down. Go up. And then blue button again, stop recording, and that's our teach frame. Now, how do we know that this was accurate? Well, there's something which comes after either you do track or teach. You can actually tune your programming. So, if we add a tune node, and in the tune node, I'll choose the trajectory. First of all, I need to choose teach. I choose the right reference frame at the bottom, it's Svetsbo. Then I choose the trajectory AOV teach test. There we go. And I open up the runtime view. And what I'm going to do now is, if I want to control the outputs, so for example the spindle and the compensation, I want to show the software when those should be active. This means that if I were to press the outputs, they would go active. Now, I can set the outputs not to be set when pushing them, which means that they will not go off once I just tell the software when to put them. So I do that. I toggle the set outputs to off. Then I open up the output tab and I press play on the tune node. And what you're going to see straight away then is that the robot moves into the first position where I was. So now, I don't know if you remember, but on the joystick setting, I set the two white buttons to forwards and backwards. What that does is that I can now go through the program like so, and actually go back and forward in my program, and then adjust different settings, okay? So, we're gonna, first of all, I'm just gonna tune the different movements. Or actually we can do like this. We're gonna tune everything at the same time. So we're gonna set override outputs. This means that whatever I do going forward from this point on until the next change I do is gonna be overwritten in terms of outputs, in terms of movement, etc. So, I'm moving in, and then we're going in here, and then boom. Right about there, I want to start the compensation, and I want to start the spindle. So, I set digital output 0, digital output 1, which are my compensation and spindle. Then I also want to override the speed because I wasn't very steady on my hand and doing it very smoothly. I wanted to do the correct speed now. So let's do about 10 millimeters a second from here on and do the override speed option, which means that from now on, until I do anything else, it's going to be doing it in 10 millimeters per second, okay? So now we'll move it in here with the forward button. See if I have a good position. I do. It's touching all the way with some leeway. Going over, touching the weld seam. There we go. And there, we're done. So from here on, I don't need it to be slow anymore. I can actually back up a little bit more to about there. And then I no longer need to override the robot speed, and I don't need the outputs anymore. There we go. And then we go all the way to the end of the program. There, my tuning is done. So what we'll do now is we'll hope that everything works exactly as we said it, and we'll just try it with playing the actual program. Because what we've done now is we've recorded a trajectory, and we've recorded a trajectory in teach mode. This is then referenced to this reference frame, svetsbord. This can be used, this can be copied, this can be translated into other locations, etc. And all these trajectories are saved, which means that we can do this in new reference frames. If we just teach a new reference frame, we can do that. We can do all of these trajectories over and over again with new tools, with new TCPs, with new joysticks, etc. The trajectories are still saved. So we open up what's called a play node. We choose teach. We choose the trajectory AOV teach test. We just suppress the tune node and we just leave that. We can open up the runtime view to see what's happening. And then we also see here in the runtime view of the play node that we can choose to set outputs or not set outputs. And let's try it. I'll take them in the order that I want them to happen. Teach, tune, play. I choose the teach and I name the trajectory AOV complex. I go over to the tune node and I choose teach and I choose AOV complex welding table I go into runtime view here, and let's see, that one is already in runtime view. The play node should also be teach, trajectory, AOV complex, Svetsboot, runtime view, there we go, set outputs. In this one should not set outputs. In the teach node, this is where we're going to start. Okay, so we're starting again, and as you know, when I press play in the teach node, it's going to tell me to calibrate it to the reference frame. So I take my HTC Vive, I put this in the calibration plate referenced to the reference frame. I hit calibrate, and I put it in my joystick, and I record. So I'll just do somewhere over here to start with, and then we're going to go down here, and we're going to go over this line over here, for example. And I'm going to go a little bit like so, a little bit like so, a little bit like so, a little bit like so. And then I made it complex for myself. I'm going to go over here, and then go over here, over here, over here, 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 here. I'm going to move over this direction, here, over here, over here. There we go. Now that's what I would call a complex trajectory to program. 56-second trajectory. Let's go into the tune node. So what I just need to do now is I go into continue. There. Now I move just with the forward button. Let's see. There we go. And let's see that I hit everything that I want to hit. So yeah, we're coming in right. So I want to be, first of all, let's see, is this in line? It is. I want to tweak this just a little bit. Then I hold the move button instead. So this button right here. I hold this and I tweak it. So when I hold it, I'm gonna just adjust it a little bit. You'll see that I can do micro adjustments, right? There we go. And from this point on, I also wanted to add the output. So override output 1 and 0. I wanted to overwrite the speed. I thought the previous speed was a little bit slow, so let's put it at 15 millimeters a second. Overwrite, and then we'll run it, go through all the different movements. There we go. Just making sure that the tuning is, that we're actually touching it. I think we are. There we go. Going around the corner to make everything fit. Yeah, there we go. Going over. There we go. Around. Moving on the side. You can see that the tubing on the, there we go, let's back up because we want to disengage the, there we go, from here we want to disengage the speed and the outputs. There we go. And then we run this to the end. And then I'm just going to adjust the cabling. There we go. Make sure that we have a little bit more room here. Something like that. And like that. That should work. Let's try it. So we move into continue. And then this is just going to play the program. So we just hit, there we go, play from play. Let's see it work. I actually made it so that I actually went too tight over here. And that's good because then I can show you how to adjust that. So somewhere around here, we're actually running too tight. So we can't move around the corner with the compensation, which is triggering the sixth or fifth axis compensation that enables it to tell us that no, something is wrong here. And that's what makes this a collaborative robot. So we're going to go back into the teach node or in the tune node, and we're going to run that from there. We're just going to put it into free drive, move it up. So we know that from the second half somewhere, we need to adjust the position a little bit. So tune AOV complex. There we go. Take my joystick. Move into the locations. So all along here we're fine. But it's somewhere along the top side where we want to go in again and see the positions, because somewhere along here is probably a little bit tight. So these first ones were fine. From here, we want to adjust this up a little bit, so let's do that. There we go. So we're giving it a little bit more room. Now doing that is probably going to have us have a little bit too much room going around the corner. Let's see what happens. Let's see, where are we now? Oh, that's fine. Maybe move it a little bit out, because we have, no, that's fine. So let's move it. Yeah, going around the corner like so. We're still touching it. Oh, here we go. Now we're in the air. Somewhere around here. So we need to move this a little bit closer. There we go. A little bit more. There we go. We still have a little bit of lead. No, we don't. So move it a little bit out. There we go. That's going to be fine. And then moving it along the sides. Still having. There we go. Perfect. Let's try it again. Continue. Boom. Show you a little bit more about what you can do with a little bit fine detailed applications. So thanks a lot and stay tuned.